Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So we are towards the end of our lecture series on CFD, applied CFD course, and we have looked at different kind of equations, Navier-Stokes equations, Rance equations. We looked at the schemes, that the stability, when to use what kind of a scheme, if the flow is highly nonlinear, if the flow has got shocks, or what kind of schemes you should use. How to basically balance between the robustness of a scheme and the accuracy of a scheme, and so on and so forth. So, this all is fine, but one very important ingredient that is missing if you want to do a CFD simulation is the boundary conditions. So, even if your all your equations are right and you are using a very accurate scheme, very stable scheme, but if your boundary conditions are not right, your either your flow will diverge or you will get an inaccurate simulation. Okay. So, in the next few lectures we will be basically focusing on the boundary conditions, because that is one of the most important aspect of your CFD simulation. Whether you will get a right solution or a wrong solution depends on how you set the boundary condition. Further, unlike a physical wind tunnel, there are some numerical considerations also which is necessary in the setup of boundary conditions. So, in the physical wind tunnel you may basically put your balls away and you may get a good solution, right. For in numerical cases often it is not convenient to put boundary very far, because that will increase your grid size drastically and hence the computational cost, right. So, we want to basically make a balance here also, that we want to keep our boundary as close to the body as possible. At the same time we do not want our scheme to blow up or get the spurious solution or the wrong solution, right. So, these are some of the challenges that we will look at when we discuss about the boundary conditions. Okay. So, if you look at a typical grid, so let us say this is my typical grid. You can think of this flow as a lead driven cavity flow, or any flow you see. Let us say if you have a backward facing step flow. Okay. So, these are kind of internal flow. So, you will make a grid like this, right. So, then in this case you will have boundary, these all regions are your boundaries, right. You have to provide the boundary condition for all these regions. Okay. Internally you can use your equations to solve it, but on all the external parts you have to provide the boundary condition. Let us say if you want to simulate flow past an aerofoil, okay, and then you make a grid around this like this. Okay, this is your computational domain, and then you make a grid which goes like this, okay, something like this. Okay, okay, let us say you have made a grid like this, okay, and of course you will have domain going like this. Okay, it will go all the way to the far field. Okay, so in this case also you have to give boundary condition on this region. Okay, this is your external boundary. Okay, and then you have to give the boundary condition on your aerofoil surface also. You can replace aerofoil by a wing, an aircraft, a cylinder. Okay, so these kind of flows are basically external flows, right. So, this is external flow and this is internal flow. Okay, for example, flow in a pipe, okay, flow inside a channel. Okay, all these kind of flows are internal flow. So, in all of these you basically require a specification of the boundary conditions on the boundaries, right. So, if you think of this is my grid. Okay, so let us say this is my grid, okay, which starts from here. Okay, these are all boundaries of my domain. Okay, and I have divided into several parts. So, let us say if you can use this IJ system. So, you have 1, 2, 3, 4, 5, 6, 7, 8, okay, 8 grid points in this direction, and similarly you can have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, basically at I equal to 1, which is basically your leftmost boundary, this one you have to specify the boundary condition. Okay, so this is what is basically blown up and shown here. Okay, similarly at I equal to 8 here, okay, I equal to 8, which is basically, I mean, the general is n. So, the far right boundary, there you also have to give the boundary condition. Okay. Similarly, for j equal to 1 and j equal to ny, let us say let us call it nx and ny, okay, you have to provide the boundary condition. So, at the bottom here and on the top here. Okay. Your boundary condition depends on the kind of flow you have. Okay. Let us say if you have an internal flow, you might have an inlet, okay, or you have an outlet. Okay. Then you can have maybe wall at the bottom. Okay. Let us say if you are doing flow in a channel, so both top and bottom. So, your flow, if you are showing flow in a channel, right. So, you have wall on top and bottom, right, and something is coming in, something is going out, right. So, this is you will have to put wall on top and bottom, and then something is going in, something going out. So, you have to give the boundary conditions for all those things, right. So, generally if you see, so if the flow is incompressible, okay, then as you know that density is not varying. So, the boundary conditions that you need is for the velocity and for the pressure. Okay. I am not talking about the turbulent flow as of now. When you go to the turbulent flow, you need to specify some more boundary conditions. Okay. For the case of compressible flow, okay, you need the velocity boundary condition, pressure boundary condition and temperature boundary conditions, and you can use this ideal gas equation or an appropriate relation between P, rho and T to get the value of rho, right. So, from for an ideal gas you can use rho equal to P by RT. Okay. So, if you know the pressure, velocity and temperature, you can get that, or you may choose that, or I do not want temperature, you can put the boundary condition on density, or you can put a boundary condition on density and temperature and not on pressure. So, all these combinations are possible, but you cannot give boundary condition for both pressure, temperature and density, because that will be over specification. Okay. Then you cannot satisfy this relation. Okay. If the flow is turbulent, then you have some more equation that you are solving. Okay. So, for example, in the Rans equations that we saw, you may have a model which is k epsilon model or k omega model, or let us say if you have 4 equation model like gamma r e theta k omega model, SST k omega model. So, for all each of these variable that you are using, the additional variables in your equation, you need to provide boundary conditions for each of them. Okay. And for if you are doing LES and DNS, okay, so we will look at LES after the boundary conditions. So, you would see that they are solving the Navier-Stokes equations as it is, right. So, if there is a turbulence in your domain, right, so you need to basically, or if the turbulence is coming towards your inlet, right. So, if this is your inlet and you see that the flow which is getting in here is turbulent. Okay. So, in that case you have to make sure that you give a provide appropriate turbulent inlet here, right. So, that is slightly difficult than Rans, because Rans you are giving the statistical quantity like the k and epsilon and omega. So, for example, this is the turbulence kinetic energy. If you have LES and DNS, you have to provide u prime, v prime, w prime, p prime and so on and so forth, or t prime, right. So, you need to basically give the fluctuations themselves rather than the any correlation. Okay. So, then it becomes slightly complicated when you go to LES and DNS, and let us say you have 10% or 5% turbulence intensity, you have to appropriately find the fluctuations corresponding to that intensity. So, that basically you get that number of 5% intensity and the whatever length scale that you have, right. We will not go into the detail. If you are doing LES and DNS, you will know about those approaches. There are approaches like you can have some kind of digital filter is one approach, okay, which gives you the correlated turbulent fluctuations. See, you have to make sure that your u prime bar goes to 0, but u prime bar is not going to 0, or u prime v prime bar is not going to 0, right. So, those correlations you need to obey. Okay. So, you have something called digital filter, or you can, what you can do is you can simulate turbulence in a box, right. So, you can just pre-compute your turbulent fluctuations. Okay, let us say you before you basically feed in here, you simulated the turbulence in a box, got this u prime, v prime, w prime, and so on and so forth, and you keep on feeding this from the inlet apart from your mean velocity, which is u bar v bar. Okay. So, that is another way, but you have to make sure that it is also temporally correlated, because these fluctuations will be changing in time, right. So, that another is homogeneous isotropic turbulence. In some cases where it is in equilibrium, there are approaches like recycling. Okay. So, whatever thing that is coming out from here, you basically rescale it and put it back. Okay. So, that approach is called recycling and rescaling. Okay. Recycling and rescaling. Okay. The idea is that let us say if you are not putting the turbulent flow also in the beginning, because of the Navier-Stokes equations, because in nonlinearity the turbulence get developed, and by the time it comes out the outlet, the flow is turbulent and correlated, and that fluctuation are feeding in back in your at your inlet. Okay. And also there are synthetic approaches, okay, synthetic turbulence approaches where you can basically generate the fluctuations. Recently there are machine learning approaches which are also coming in to give you this turbulent fluctuations. So, that is an additional difficulty in the LES and DNS, that you do not only give the boundary conditions for the mean flow, but also for the fluctuations. Okay. So, we will not discuss this part in the boundary conditions. If you are interested, you can look for appropriate books, and there are a lot of literature where you can see how to provide the inflow boundary condition, turbulent boundary conditions for the LES and DNS. Okay. One more important point, that typically we use this conserved variables in the compressible flow, especially in the compressible flow, right. But giving the boundary condition, let us say for rho u and rho v and rho is not straightforward. So, what we will do, we will basically give the boundary conditions in your primitive variable, which is rho u, p and t, and then they will be converted to rho, rho u, rho v and rho e for the iteration. Okay. So, your equations will be in this, but you will give boundary conditions in this, okay, on rho u p t, and that you need to do every time. So, basically in every loop, in every iteration, you have to convert your conserved variable to a primitive variable, okay, and then provide the boundary condition to the primitive variable, convert it back to the conserved variable and run in the loop. Okay. Now, if you look any typical software, okay, you will have several boundary conditions available for you to implement, right. So, first of all, you should know what is your flow like. So, that is very important to know what you are going to simulate, okay, where there is a wall, whether there should be flow coming in, where the flow should be going out. Okay. So, typically let us say if you look Fluent or OpenFOAM, these kind of softwares or any software for that matter, there are some boundary conditions which are very common. For example, there will be a pressure inlet and corresponding there is a pressure outlet. Okay, if the flow is coming in from some location and going out from another location, okay, then you have to give the pressure inlet and pressure outlet. Okay. So, this is general, this is there for compressible flow, incompressible flow, all kind of flow, subsonic, supersonic, hypersonic, although the implementation is slightly different, we will discuss that later. Okay. For if the flow is incompressible, you have got velocity inlet, this is not there for compressible. Okay. We will look for the region when we discuss about inlet and outlet. If the flow is compressible, then you could use mass flow inlet, basically this is rho u a, okay. Because your density is also varying and velocity also varying, right. So, instead of using the velocity inlet, you will be using the mass flow inlet. This can also be implemented for incompressible flow, but I mean it serves no different purpose than the velocity inlet, because ultimately your rho is constant here. Okay. And then if you have an outlet, you can have kind of outflow. Okay. It can only be used with the velocity inlet, it cannot be used the pressure inlet. Okay. So, that is one requirement, that if you have pressure inlet, you cannot use outflow, because the pressure gradient that you want in the flow is not achieved if you are using a outflow with the pressure inlet. Okay. So, in the pressure inlet you are specifying the pressure, in the outflow you are making sure that all the gradients are going to 0. Okay. It is basically very far from the body. So, okay, when we have the detailed discussion, we will come to this very soon. Let us discuss what are the boundary conditions that are available typically. For the compressible, you have the pressure outlet, but then you also have an option of non-reflecting boundary condition. Okay. So we will discuss these things also later. Okay. If you have a wall, you can have a slip wall, basically things are slipping on the wall, it is not sticking to the wall, or you can have no slip wall, which is a more physical condition where the particles on the wall are sticking. Okay. Basically the velocity is going to 0, identically 0 on the wall. Okay. Then there is something called symmetry. Okay. So if your domain is symmetrical, so let us say if you are trying to simulate flow in a channel, okay, and you are basically doing at doing for a mean flow or at a Reynolds number when the flow is identically symmetrical. Okay. So it is like let us say your flow is looking like this, okay, which is symmetric around the 0 axis. Okay. So that what you can do, you can basically ignore the top part, okay, and do the simulation only for the half part, right. So how does it help you? It basically reduces your computational effort, right. In 2D it will become just half, okay. In 3D you will have more savings because you do not have the third dimension also. So basically it reduces your computational effort a lot, but it has to be utilized with care. You have to make sure that the flow is really symmetric. For example, if you take flow past a cylinder and Reynolds number let us say 100, so your vortex setting starts, okay, and sometimes it will set from the top, sometimes set from the bottom, okay. So simulating this kind of flow with symmetry is not advised. In fact, you will get wrong results if you just take the half the cylinder, okay. So on the other hand, let us say Reynolds number is very low, Reynolds number is 10, where the flow is symmetric from both the sides on the cylinder, then you can use the symmetry boundary condition, alright. So you have to use this boundary condition with care. So in this case, you can if you take the example of channel, you can use the symmetry here on the top, you can use maybe slip or no slip, okay, at the bottom, and then the flow is coming in from here, so you can use some kind of inlet here, and flow is going out from here, so you can use some kind of outlet or outflow there, okay. So remember this terminology, outlet is different from outflow, okay. These are the names which are used in the literature, and they have got some physical meaning assigned with why they are called outlet or why they are called outflow, okay. There is another also very popular boundary condition which is called far field, and this is used typically for the compressible flow. So let us say you have a cylinder here, okay, and you create a domain which is very far away from the cylinder. So if the cylinder diameter is let us say 1, then you make it maybe 20 times or 50 times the diameter of the cylinder, and then the implementation of boundary condition is easy. We can use a boundary condition which is called far field, okay. This is only for the compressible flow, okay. You can also have the periodic boundary condition. So what I am showing you here is a series of turbine blades. So if you see any turbine, so the blades are basically mounted on a shaft, okay, and you can see that if you want to simulate the entire shaft, you have to simulate hundreds of blades or 200 of blades, okay, whether in compressor or in turbine. So instead of doing that, you can basically just take the region between the two blades and say that okay, whatever is happening on the top is basically repeated from what is happening at the bottom, okay. So it is assumed that I mean the flow is symmetric on top and bottom or cyclic on top and bottom. So in that case, you can use the periodic boundary condition, okay, on top and bottom, and that also helps you basically reduce the computational cost a lot. Okay, let us say that if I am trying to simulate a wave which is basically repeating, okay, like this, okay. So instead of simulating a very long domain where the wave is repeating, what you can do, you can truncate it somewhere, okay, maybe here and maybe here, and then you can use the periodic boundary condition here, okay. So that really helps you in the saving the computational cost, okay. So here I am saying it's there are two kind of periodic boundary condition. One is the translational, another is rotational, okay. So translational is for example, if it is a linear cascade and you know what is the distance between the two, okay, you just shift the property from here. So you want to copy this value to this value or this to this value. So you know what is the distance here, let us call it d. So, you basically use the values here, I mean shift the value here by d. Okay, you can have something on the rotational. Okay, let us say if you see a burner. Okay, so you can have a burner here. Okay, then here. Okay, and let us say you have several burners like this. Okay. So, instead of basically simulating this entire thing, you can may select to basically choose a domain which is like this. Okay. So, instead of choosing the entire domain, you can just choose a domain between this and then use a periodic boundary condition here and here. Okay. So, then you can use the rotational periodic here. You know the theta here, and at what angle you have to repeat it, you can use the rotational periodic boundary condition there. Okay. So, now let us take the boundary conditions one by one. So, we will go to inlet and outlet in the next class. Today, we are going to discuss boundary conditions which are very simple to implement and which does not have any ambiguity. So, for example, the boundary conditions like wall boundary condition, okay, symmetry boundary condition, and the periodic boundary condition. Okay. So, there is no ambiguity in these boundary conditions. But if you go to let us say the inflow and outflow or inlet and outlet, there are many ways you can implement this inlet and outlet, and you have to be very careful for which variable you are basically specifying. Okay. For example, you cannot specify both velocity and the pressure at the inlet or outlet. Okay, that is kind of over specification. Okay. So, today we will discuss these simple boundary conditions, wall, symmetry and periodic. So, the wall is very easy. Okay. So, let us say if you have a surface here, okay, which is wall, okay, and then you have a flow which is happening on top of this. Okay. So, what the wall boundary condition says, so that you can take the normal component and the tangential component of the flow, right. So, if the normal component is 0, that is called the no penetration. Okay, that means your u normal is 0. It has to be satisfied for every wall, okay, whether it is slip or no slip. Okay. So, the particle cannot penetrate to the wall. Okay. So, in this picture if you see, your u normal is going to be 0 for any case. Okay. Now, comes the part which is u tangential. What happens to the flow which is tangential to the surface, right. So, if the flow is no slip, okay, then the velocity of the particle on the wall will be equal to the velocity of the wall. Okay. So, if the wall is stationary, it has got no motion, then the velocity of the particle on the surface will be 0. Okay. So, that is called the no slip boundary condition. So, in this no slip will also be ut will be equal to 0. But there is also an artificial boundary condition, and it may be physical also at very high Mach number, okay, very high Mach number. So, where the flow is not sticking to the surface. Okay. So, in that case what will happen, that your ut, if I can call this ut on the wall, okay, will be equal to the free stream velocity or the velocity on top of the wall, okay, the velocity on top of the layer, right. So, your ut will become the value, if let me call it u. So, that will be equal to let us call it u infinity. Okay. So, your velocity, the tangential velocity is not 0 if it is slip condition, right. Remember, if the wall is moving at a velocity of u, okay, then in the no slip the ut will be equal to u wall. Okay. If the wall is moving at a velocity of uw, recall the example of the lead driven cavity. Okay. So, it is a very simple example and with well defined boundary condition, all three surfaces are wall, right, and the top one is moving at a velocity u, right, let us call it uw here. Okay. And then because of this vortex forms. So, all 4 you will be applying the no slip boundary condition, but in this case here u will equal to 0, v equal to 0, u equal to 0, v equal to 0, u equal to 0, v equal to 0, and here u equal to u wall and v equal to 0. Okay. So, this is also no slip, okay, this is not slip, because here the wall itself is moving. So, the no slip says that the particle acquires the velocity of the surface, that is all no slip means. Okay. So, the slip wall or the inviscid wall. So, slip wall is typically used in numerics to study the viscous effects, right. So, what you can do for some surface you remove the viscosity, use the slip condition. Okay. So, if you do flow over a flat plate, okay, and if you use the slip condition, so your transition velocity is not slipping here, the u n I mean the v is equal to 0, but u is not equal to 0. So, you will not get a boundary layer. So, you will get a surface which will be like this, okay, no boundary layer. Okay. So, this is your slip condition. Basically, it is slipping on the surface, right. On the other hand, if you use the no slip boundary condition, then what will happen? You will get a boundary layer like this. Okay, this is your no slip condition, because the velocity is 0 here on the surface, and then the velocity will increase, and at the boundary layer thickness or little above the boundary layer thickness, it will acquire the free stream velocity, right. So, the no penetration is satisfied. Once again, the flow slips on the wall, the tangential velocity is equal to u, and there will be no boundary layer, typically used with the Euler equations or the inviscid equations. Okay. In those cases, you should not use the viscous wall, but the no slip wall. Okay. Second is the no slip wall. Okay. Here both the no penetration and no slip are satisfied. Okay. Both the normal gradient as well tangential velocity gradient are 0, the boundary layer will develop. Okay. And basically you will satisfy for both the velocity, but what about the pressure and temperature, right. Temperature specifically if you are doing a compressible flow, right, or if even in incompressible flow if you are using a thermal equations, okay, or I mean you are putting some source term. Okay. So, the normal pressure gradient is set to 0 on the wall. So, if you have wall, you use the normal pressure gradient to 0. We will see how you do that numerically, how you implement that in your code. For the temperature boundary condition, you have two kind of walls, one is adiabatic wall, another is isothermal wall. Okay. When it is adiabatic wall, that means your the gradient is going to 0, there is no wall flux, right. So, your temperature gradient is going to be 0. Often we use the isothermal wall, let us say you heat the wall or you cool the wall. So, you are basically fixing the temperature of the wall. Okay. So, then you have to set the temperature at the temperature of the wall. So, they are called the isothermal walls, right. And once you know the pressure and temperature, you can calculate the density using the ideal gas law or any relation which relates these three variables. Right. Now, how do you implement this dP by dN equal to 0 numerically in a code, right. So, if you look at this picture, so this is my I equal to okay, I and j is equal to 1, okay, and let us say the second surface is j equal to 2, okay, and we want to get dP by dN, in this case dP by dy, if your coordinate system is like this x and y at y equal to 0, which is basically dP by dy at j equal to 1, right. So, what you can do, you can use the Taylor series expansion, right. So, if you write it at 2, so you can use P I at a given I, j plus 1 is equal to P I j plus delta n, which in this case is delta y, whatever distance you have, this is the delta y, okay, into dP by dN and then higher orders, right. And then what you have to say that my dP by dN goes to 0, okay. So, that means your the value at ij, okay. So, P I comma j is equal to P I comma j plus 1, in this case P I comma 1, which is the value at the wall, is equal to P I comma 2, right. So, you know the value of pressure next layer, on the next layer, just use that value, okay. This is the first order approximation, okay. Let us, you can have the wall on top also, right. So, let us say if I call this ny, okay. So, then you will have P I ny is equal to P I, and then you have to take the value from the layer just below that ny minus 1, right. So, this is basically the gradient goes to 0. These conditions are also called the Nyman conditions. Okay. I am sure you know the Dirichlet and Nyman conditions. In Dirichlet, you apply the basically fix the value, in Nyman you fix the gradient. Okay. So, here we are fixing the gradient and making sure that dP by dy is going to 0. Okay. You can also have the second order approximation. So, you can take the 2 layer. So, this is my wall, okay, and I can take one layer here. If this is my j, this is my j plus 1, and I am taking another layer which is j plus 2, right, and then you write the Taylor series for j plus 1 and j plus 2, okay, and then what you do, you can eliminate this del 2 p by del n square, because you want a second order relation, just to make the boundary condition more correct. Okay, so what you can do, this is 2 square delta n square by 2, so you can multiply this by 4 and then subtract, okay, multiply by 1. Okay, so a into 4 and b into 1 minus b into 1, so that will get 4 p I j plus 1 is equal to 4 p I j plus 4 delta n delta p by delta n, and that's like p I j plus 2 is equal to p I j and plus 2 delta n delta p by delta n. So, you can get the delta p by delta n from here. Okay, that will become I think this will become 4 p I j plus 1 minus 3 p I j, okay, and minus p I j plus 2 by 2. Okay, I hope I am correct. You can verify this. Okay, so basically what I am saying, that you will get a relation which is j plus 1, j plus 2, j plus 1 and j and delta n, right, and you can set this value to be 0, and that is how you get the value of p I j. That is the purpose, you want to get the value of p I j, right, this is the p I j. So, you will get the value of p I j. So, you are using the value of not only the first layer, but also the second layer to get the value at p I j, right. Next is the symmetry boundary condition. So, as I told you, I gave you an example of channel, but here you can see that let us say you have a flow over an aircraft and you are looking for basically a mean flow, which is basically symmetric to this airplane. So, for example, the plane is something like this, okay, which is basically completely symmetric to what we have here, okay. So, something like this, okay. So, and the flow is completely symmetric to this, the mean flow at least, okay. So, then you can use the symmetry boundary condition. You can forget about the top part here and put the symmetry at the center and do this, okay. So, here also if it is I mean the cross flow, okay, I mean on a cylinder, okay. So, you can only solve half of this if the angular attack is 0. So, again you have to be very careful what kind of flow you are simulating, whether there is an unsteadiness in the flow. This boundary condition cannot be, for example, used for LES or DNS, okay. You cannot use it because the flow is changing instantly, okay. So, there will not be any symmetry, okay, even at decent Reynolds number, okay, decently high Reynolds number. But for the Rans flow or very low Reynolds number flow, when the flow is symmetric, then you can use this kind of boundary condition, okay. So, only applicable in symmetric flows, you have to be very careful, not unsteady like vortex shading, LES or DNS. So, this implementation wise numerically it is very close to the free slip boundary condition, okay. It is like an inviscid wall, okay. So, what we are saying that once you have a symmetry, okay. So, let us say this is my symmetry, okay. So, this is my symmetry, okay. So, there is no flow occurring across this. So, there V is equal to 0, sorry, V will go to 0 and there cannot be any flux, okay. So, that means your del u by del y equal to 0, del p by del y equal to 0, and that is how you calculate the value of u and y, u and p and v, everything here at the symmetry plane, okay. So, set normal flow to 0, set normal derivatives to 0, okay. The additional way to do it, that because there will not be any shear stress here, set wall shear stress to 0 at the symmetry plane. So, that is how you can obtain it. And as I was saying, that if you look at the implementation of the slip boundary condition, okay. So, here also what you do, you set V equal to 0 because there cannot be any penetration, and for others you put the gradient equal to 0, right. So, implementation wise the sleep boundary condition and the symmetry boundary condition both are similar numerically, but in terms of physical concept they are completely different thing. Okay, symmetry is used to basically reduce your computational cost. Okay, finally, look at the periodic boundary condition. Okay, so here you have a series of turbine blades, and as I was showing the picture that instead of doing this for the entire blade, you can just choose one blade, and then you know that what is the spacing between the two blades. You make your grid in such a way that the spacing is honored, okay, on top and bottom. So, this is the spacing which is d, which is equal to the spacing d here, right, and then you put the periodic boundary condition on top and bottom, okay. So that it will reduce your computational cost a lot. And how do you implement it numerically? So, a very simple way to think about it, I mean is think of a ring, okay. So, if this is your ring, okay, so this is your 1, 2, 3 and keep on going, and all the way it will come back to n minus 1, this is n, right. So, whatever is 1 is also equal to n, right. So, if you now you open it up, so now you will have 1, 2, 3, n minus 1 and so on and so forth, right. So, if you would have continued, then this will become your n plus 1, right, and this you can call it maybe 0, right. So, your 0 value is equal to n minus 1, okay, and n plus 1 is value equal to value of 2, right. In some of the code the way it is implemented is, instead of basically closing it here, you go and basically you go like this. So, this is your 1, 2, 3, okay, and this is your basically an if you don't. So, for this you need to use ghost conditions, right. You need to have extra cells which is beyond 1 and n, right. So, if you do not want to do that, so what codes do is you can call it, this one is n and this one is n minus 1, right. So, you need the value at boundary 1 and you need the value at boundary of n, right. So, u 1 you can call it as u n minus 1, which is the internal node, and u n is equal to u 2, right. So, what we did, we shifted by 1, right. So, 1 became 1 minus 1 and n become 2. So, you do not need any ghost conditions in this particular case. Okay. So, with this we will stop the class today. In the next class we will look at the several implementation of the inlet and outlet boundary conditions. Okay. Thank you very much.